Hello again. This this is the second part of the video that concentrates on or focuses on solution stoichiometry. And I've already worked out a problem to show you. So please write this problem down or follow it from my screen. It's a good idea to write it down because I'm asking you to solve something with it. So I have two solutions. One is prepared as silver nitrate aqueous. The concentration is 0.20 molarity, which is 0.20 moles per liter. The quantity of that solution is 15 milliliters. And we are mixing that with a second solution, 0.30 molarity calcium chloride, and 35 milliliters of that. So here we have two chemicals in the aqueous state. They're both soluble. And when we mix them together, a reaction takes place, which I've written below the mix container. So if this is my mix container, and a chemical reaction takes place, so let's write it here. Reaction takes place. And in this reaction, you should know these reactions. This is a double replacement reaction. Double replacement. We also call it double displacement. And in this reaction, the silver ions, they precipitate along with the chloride ions, forming silver chloride. And the calcium and nitrate ions, they are essentially spectator ions. So that's why I wrote them in the aqueous state. So they don't precipitate, they just stay suspended. But I'm going to make the problem a little bit more involved in terms of the situation that we have. So because we are mixing two chemicals with a known concentration molarity and two different volumes, you essentially need to worry about excess limiting situation here. As you learn in your introductory chem and your general chem courses, that you really need to know which is the excess reagent, the limiting reagent, because the limiting reagent limits how much reaction takes place. I don't know if calcium chloride is going to limit my reaction or silver nitrate, but we can determine that. And for the first part of the problem, I'm asking you to calculate mass of silver chloride formed. So go ahead and use whatever technique that's easier for you to determine the limiting reactant first, and then determine the mass of silver chloride. Mass units are commonly in grams, so you're trying to figure out how many grams of silver chloride is the product here. And then watch the video again, so pause the video, solve the problem, and watch the video and see my technique of using an ICF table. I stands for initial, C for change, final. So there's 3 lines that you fill out, and it's a very complete way of calculating the stoichiometry of this problem. So I'm going to explain this technique to you because this is a technique we're going to be using later on too. So it's important to understand how to do it with this technique as well. So here it is. I'm writing my reaction again. So I'm assuming you solved the problem already. I'm writing my reactions again. And my reaction needs to be balanced for us to do any kind of calculation. So in order to balance it, we put a subscript 2. I'm sorry, I didn't do that correctly. So a subscript 2 next to silver nitrate, and a subscript coefficient 2, not a subscript, I'm sorry, a coefficient 2 next to silver chloride. So the reaction now appears to be balanced. 2 silvers on each side, 2 nitrates, 1 calcium, and 2 chlorides. So we can go ahead and solve the problem. Now, these tables, the ICF tables, they can work with molarity units. So every entry here is going to be molarity. Like we're going to be filling out these entries for everything. Even though there is essentially one product that's formed, we're going to fill out all the lines here. And next we're going to, the table, I was going to say, the table works with molarity units, but the molarity unit in the table has to be the molarity that's in the mixed state, or what we call the initial molarity. Initial molarity would have to be mixed because, taking you back to the problem, the silver nitrate gets diluted by calcium chloride because you're adding 35 milliliters of calcium chloride onto silver nitrate. And calcium chloride gets diluted by silver nitrate. So the initial molarities will be different. But the other way you can work with this, so we can calculate the initial molarity, but the other unit I wanted to work with is the unit of millimoles. So we can work with mole unit or millimoles. Millimoles are a bit easier because, as you recall, molarity is moles over volume of solution in liters. So moles are calculated by taking molarity and multiplying it by volume. Well, if my molarity is in units of moles per liter and my volume, I put milliliters. Look what happens. The liter cancels with liters and the milli sticks next to moles. So it becomes millimoles. So these will calculate to be millimole. Millimole numbers are easier to deal with because the numbers are typically higher because the unit is smaller, and therefore it's more common sense to look at the numbers and make sense of it. And so let's go ahead and calculate. Please have your calculator ready. I want you to calculate millimoles of each of these reactants. So again, you have the equation in front of you and you have the volume and concentration of each reactant. So to make it more visual or easier, 0.2 molarity of 50 ml. So let's go ahead and write here 0.20 molarity, and we have 50 milliliter. And calcium chloride, we have 0.30 and 35 milliliters. 0.30 molarity and 35 milliliters. So now our job is to get millimoles. So it's quick by taking molarity, multiplying it by the volume in milliliters. The first one will give me 10. And I'm going to go ahead and write it once. The whole table is in millimoles, just to remind you, but I won't write it for the other quantities. So the other one is 0.3 times 35 is 10.5. 10.5 millimoles. And of course, I don't have any millimoles of the products that I'm mixing in, and so it will just be 0. Now, I need to know the change line. So the line that C stands for change. And in order to get the final line, we want to get it by taking the initial line plus the change line. Therefore, my change should be positive or negative. Positive is for a situation that a chemical is produced. So you put a positive sign next to the millimole. Negative is for a situation when a chemical is reacted. So this way, this plus and minus will essentially work itself out correctly in sign when you do the final line. So we need to figure out which is the limiting reactant and which is the excess. So a quick way that I like to teach my students is to look at these coefficients. So let's go ahead, and this coefficient is 1. So the ratio of silver nitrate to calcium chloride is 2 to 1. So you need twice the silver nitrate with half the calcium chloride. That's how this works in mole basis. So when I want to do a quick calculation, you have to do 2 calculations to determine what's excess, what's limiting. So let's start with the 10 mole of silver nitrate. So I'm not going to write this down, but I want you to do it. Maybe you should write it down just to be sure. So if you got 10 mole of silver nitrate and you want to figure out how many millimoles of calcium chloride is going to be needed, you essentially have to divide it by 2. So it's like taking the 10 millimoles and multiply it by a ratio of 1/2, because you need, of course, less calcium chloride, in this case by a factor of 2. So the 10 millimoles multiplied by a ratio of 1/2 gives you the requirement of calcium chloride. So if I take the 10 times 1/2, you get 5 millimoles. So you're going to be reacting 5 millimoles of calcium chloride with the 10 millimoles of silver nitrate. And I have more than enough. In this case, I have 10.5 millimoles. So that is the correct one. Now, you do have to do the other calculation as well, just to be sure. Sometimes it works the other way around. If you start with 10.5 millimoles of calcium chloride, how many millimoles of silver nitrate do you need? In this case, your ratio becomes 2:1 or 2/1. The 10.5 has to multiply times 2 divided by 1, because when you go from a lower moles, this is 1 mole, this is 2 moles. When I go from lower to higher, my ratio has to be multiplied. If you're going in this direction, you're going to be multiplying by 2/1. If you go in the opposite direction, you need to multiply the 10, that's what we did, by 1/2. So the 2:1 ratio, so if you take the 10.5, multiply it times 2, you get 21. I need 21 millimole of silver nitrate. I don't have 21, I only have 10. So that calculation does not work out. So let's go ahead and work with the correct calculation. With the 10 millimole of silver nitrate, I'm going to be needing only 5 millimoles of calcium chloride. So all of my 10 millimoles are going to react. So I'm going to write -10. Remember, change line for something that reacted is negative. Now, how much calcium chloride is going to react with 10 millimole of silver nitrate? Do that calculation again. So you're going from silver nitrate to calcium chloride. Your ratio is 1/2. So take your number, multiply it by 1/2 factor, because you're going toward less moles. The factor has to be 1/2, which means 5 millimoles. So I'm going to react -5.0 millimoles. So I found my millimoles reacted. Now let's focus on millimoles produced. So because this is limiting now, remember we figured out this is the limiting. So you can now work with the 10. So if you have 10 millimoles reacted of silver nitrate, what is your factor? What do you multiply by? The factor is 2/2, because you have 2 mole of silver chloride produced with 2 mole of silver nitrate. Produced from reacting 2 mole of silver nitrate. So essentially your factor is just 1. 2/2 is just 1. So you're going to produce plus 10.0 millimole of silver chloride. And the calcium nitrate has a different factor, because you're going from 2 to 1. Let's put a 1 here so you see. So 2 mole of silver nitrate makes half as much calcium nitrate. If you start with 10, you multiply it by 1/2 is the factor. So this factor method is very powerful and very quick. If you can handle that, it's the best way to solve these problems. So you are going to make plus 5 millimoles of calcium nitrate. So here it is. Now, calcium nitrate technically is not a product because the ions are floating in the solution. Silver chloride is the product because you have a solid product formed. But you are making 5 millimoles of calcium nitrate once you use up 5 millimoles of calcium chloride. So the table is showing you the moles or millimoles of ions in the solution correctly as well. So that's why it's a good table to keep in mind. So the final line is just I plus C. 10 minus 10, 0. That's why it was limiting reactant. Silver nitrate, there's nothing of it is left over. So 10.5 minus 5, it will be 5.5. So this is essentially the I line plus the C line. And 0 plus 10 is just 10. 0 plus 5 is just 5. So here it is. I found all the ingredients within the problem in terms of millimoles. And remember, you have a total volume. Let's go back up to the picture. You have 85 milliliters. So this whole volume is 85 milliliter because you're mixing 35 milliliters of calcium chloride with 50 milliliters of silver nitrate. So I have my moles, I have my volume, and you can get molarity. Remember, molarity is moles per liter, or very conveniently, millimoles per milliliter, because we have our milliliters of total, and dividing millimoles by milliliter, you get moles per liter. Millis cancel, which is the same thing as molarity. So that's why millimoles are very convenient. So I found the millimoles of silver chloride. So to find the grams of silver chloride, let's go ahead and do this part. You have 10 millimoles of silver chloride. We need molar mass of silver chloride. Silver has 107.87 and the chloride is 35.45. That gives me 143.32 grams per mole. And I need to just get grams, so the milli has to get cancelled away. So I just want grams. So notice, mole goes with moles. Milli is worth 0.001. So you write it like that, and milli cancels with milli. This is again a very useful method that most people don't utilize, but I find it very useful. And the other option would be for just, getting, because if you look at your relationship, you would have milligrams. So you can just do 1000 milligrams per grams, and that cancels your milligrams. So essentially this is the same thing as this, because you're multiplying by 0.001 or 1 over 1000. So let's do that. So 10 times 143.32 times 0.001, that's 1.43. Within 2 sig fig, it would be 1.4 grams. So I found my mass of silver chloride. Now let's put a second part to the problem and find concentration of all ions. And some people get confused over this part. So part B is calculate concentration molarity of all ions after the reaction. So I go back to my millimole table, ICF table, and I can see that the silver nitrate portion that we started with, the silver nitrate, the silver ion essentially was the limiting quantity, and that went down to 0. But there is some nitrate that's excess here, and that's what the calcium nitrate on the right side shows, that you have 5 millimoles of calcium nitrate. And you have calcium ions here, and let me back up and let me actually help you see it visually. So in this case, the silver nitrate was the limiting quantity. It went down to 0. And so if you look at your ions, your spectator ions that you can cancel away from this process, the spectator ions are nitrate ion and calcium ion. And so the product is just silver chloride. The net ionic equation of this reaction is just silver ions plus chloride ions will give you silver chloride. And so we can keep that in mind, but also keep in mind that you have calcium chloride that's excess here. And you can see that there is a leftover calcium chloride at the end. I'm going to circle that for you, 5.5 millimoles of that. and you have